my origin story. Oh, that doesn't work. I'm over here. So HeinLab. I am formally trained very much like Schindler Lab originally. Like I was Schindler, well, mechanism and methodology. So I started my degree doing asymmetric catalysis and asymmetric synthesis. So it's basically reaction discovery from a very kind of put it on, let's see, try to figure out why a reaction is or isn't working. But you do this very much from a sort of a hunt and peck kind of point. So I started in the very classical version of methodology where you look at literature, you try to devise a strategy, and you do a new reaction based on what you've seen somebody else can do. That led very heavily into mechanism. So my postdoc was with Barry Sharpless at Scripps. And while I was there, I actually was part of the team that helped to recruit Donna Blackman. So Barry Sharpless, do you guys know him by name? Donna Blackman. So the interesting thing about those two, Barry Sharpless is known for asymmetric synthesis. You know, this is reaction methodology, and ligand accelerated catalysis is a big part. More recently, from the chem bio world, click chemistry, and sort of fusion of molecules. That's kind of there at that point. The thing I learned from Barry more than anything else was that kind of the instinctive part for why a reaction may or may not work, but it was without the practical part. In other words, if you have a reaction that isn't going to work, what do you do? And without kind of a Perrin level of encyclopedic knowledge of all chemistry, it's difficult, right? This is something that's kind of like a vampire where you have to spend many, many, many years in the field to kind of understand what you might try. Mechanism is what I learned from Donna Blackman. So she's actually a chemical engineer, not an organic chemist. And that's kinetics. That's understanding how to probe a reaction and listen to it and giving the analytical skills. So the thing I was joking about Earth and Ocean Sciences, most of what we end up doing in physical organic chemistry is equal parts organic synthesis, equal parts analytical chemistry, and equal parts statistics, mathematics. Because what you have to do is blend these pieces together where it's no longer about worst day of any PI. I tried this reaction. Okay, well, what happened? It didn't work. How do you quantify it didn't work, right? It's turning it into, well, what happened? What was the concentration? What was the yield? What happened to the rest of the molecule? So this is the work that we ended up doing. A lot of that part leads over to catalysis and building new hardware and tools. So the other thing that happens in my lab is a lot of hardware development. A lot of the measurements that we need to do not have really good pieces of equipment to make that measurement. So this is where more recently in our area, we've gotten into what's called autonomous research. So this is where we're now fusing data science, robotics, and AI in order to do cool things as generated by ChatGPT. The fun thing I like to emphasize, what we are doing as novel as 1988. So this is actually a Chem and Eng News article talking about, again, you can see by the 80s graphics, the amazing new world of robotics in the lab. We were doing this 80 years ago, or like 40, 50 years ago. This is a standard cobotic arm that looks a lot like the types of thing you see in my lab now that was being seen as the novel next technology back in the 80s. The difference now with what we are doing, technologies like this, at that time, an arm like that might have cost the equivalent of like 5 or 6 different PhDs. Now it's about $20,000, $30,000. So the accessibility of a lot of this hardware is massively expanded. And again, talk to Lucy. The type of people in our lab have just as much skill with glassware as you do with Python encoding. So it's something that I want to make sure that we bring to the class here is the ability to use some of these data science tools. If you're interested in the general area of self-driving laboratories, there's a couple of really good articles recently written about this topic, what it actually means, what the hardware has to be, and more importantly, the kinds of things you need for each one of these components. Again, I only bring it up because what we end up doing in physical organic chemistry is really on this kind of measurement side of things. We have to actually be able to not just run the chemistry, but also make analytical measurements about if the measurement that you did is actually accurate. For a broader component of what's happening in my lab and also somewhere this sort of ties pieces together, we're part of what's called the CFREF, the Canadian First Research Excellence Fund. We're running a larger project with the Acceleration Consortium in the University of Toronto. We're responsible for this area here, which is the scale-up part. So have you guys heard of process chemistry? What is process chemistry to you guys?
So when a company discovers a new molecule, they need to scale it up for further tests. So the development of chemistry that works in a larger scale, like industrial kilograms.
Absolutely. Any other additions to that? That's a good center point. Like it really focuses on manufacturing. The added challenges that go along with process chemistry means you're no longer allowed to necessarily use any reaction any time, because sometimes it's safety. Certain reactions cannot be run at scale because of energy, consumability. The number of times we've been called in because somebody did a batch reaction, a simple Suzuki, where the comment was, we used all the palladium in the northern hemisphere and the reaction stalled, now what do we do? So there's an added level of complexity that goes on to this just in terms of scale and practicality. And that's where all these different pieces come together. This is why it kind of works this way. Something you'll see about how I like to structure discussions about reactions, any reaction you do has to be broken up into these three key areas. You've got the stuff you need to do before you run the chemistry. So that's things like calibrating the stability of your ligand, calibrating your HPLC or whatever your analytical technique is, making sure that your NMR is actually giving you quantitative data, right? So there's a whole host of stuff you have to do to measure a reaction before you even do the reaction. Then there's the reaction itself. You have to execute it. You need to watch what happens during the reaction. You're measuring usually real time to get some kind of kinetic. You're looking at change over time. And then finally, work up an isolation. So anybody who's done small scale reactions, have you ever done something where TLC said everything was fine, then you do this and you have goose egg? This is a reality we've all lived with, right? And that's where understanding that each of these problems is part of our physical organic journey. If you screw up this, your measurement's wrong. So you may be led astray because your instrument was lying to you. If you screw up this, the reaction might have been fine, but you threw out your product or it degraded on you. And the thing is, if you completely focus on, I got 0% yield, it must have been this problem that the reaction execution is wrong, you're gonna be wasting a lot of your time. So a lot of the things I wanna focus on is when reactions do and do not work, which one of these buckets is the thing that's lying to you? The biggest thing I want you guys to start thinking about is a language around interpretation, expectation, and assumptions. Something I like to try and enforce as we go through this is, if you're trying to make a conclusion based on the data you're having here, what are the assumptions that you have to make in order to make that conclusion possible? Sometimes what you'll see is your outcome here, what this reaction is telling you, may be wrong only because the assumptions you've layered on top of it. And you have to be able to differentiate between the two of them. So it's something I want to focus on as we go through. So this is a nature synthesis opinion piece that we did last year. And the context was to emphasize this. And again, I know that if you've seen any lectures by Donna or other people, you may have heard the same sort of gripe. If you do a reaction, in this case it's a Suzuki reaction, you're making 3 possible products, and if you look at it, this might be, from a single endpoint yield, the distribution of your products. And based on this, we can say, okay, light blue is currently winning. If we're trying to execute this reaction, in this case, we're trying to do a selective Suzuki reaction between that aryl bromide and this boronic acid, because we want to make purple, we're actually not doing well. That's the lowest concentration product that we actually have here. And this is only because that's our overnight. Now, the joke for most organic chemists, especially medicinal chemists, you only really have 3 time zones. There's overnight, over lunch, and over coffee. And the number of times that, and again, if I earn nothing else from you guys, by the end of this course, I want you guys to promise me, when you set up a reaction, the very first thing you do once it's up and running is measure what's happening. Because the number of times the reaction's done the second that you add everything together is insane, and then you wait this long and there was no point. Because if you look at it, purple, the thing you care about, was fine and never changed that entire time through. All you did by adding this extra time is make the reaction more dirty. What we end up doing, and hopefully by the end of the course, this is how you should see a reaction. It's the complete moment-by-moment distribution of every trend of every component. Once you have this kind of data, this is why the data science thing actually helps. If I'm trying to train an AI model based on this picture, you're overfitting the data, you're making conclusions that may not be relevant to your actual system. If you have something that is more robust, more detailed, now you have the moment-by-moment GPS trends of what's happening in a system. This is the same joke as kind of like, imagine training your Tesla to drive from place to place using historical traffic data and hoping that you don't run over grandma. Like, that's the moment-by-moment data that you should be using. So the thing is, getting there takes time. You need to understand what those curves mean, how do we fit them, what's the physics behind all of that, and how does the measurement work. Again, from the purpose of a process chemist, we wish we could take a reaction and immediately look at a profile. The problem with that is that there's a lot of stuff that goes wrong in between. So, especially now, most reactions do not fall into that nice, simple liquids reacting with liquids at room temperature. Sometimes you have extreme temperatures, you have solids, you have multiple phases, you have extreme temperatures and pressures, you have materials that basically not only defy the analytics, but also defy the ability to sort of do the reaction without any changes. Understanding what these liabilities are and how to deal with it is something we'll focus on as we go through our measurements. We've done this by adding a layer of robotic sampling and analytics, so this is where that technology bridge is necessary to actually understand the physics. Not only that though, we need to do this. Where's my thing? There we go. You have to be able to do your measurement on your system as if your measuring tool was never there. So does everybody know Schrodinger's cat? If your measurement changes the outcome, then it was a useless measurement. In other words, okay, so quick example. Grignard reaction, people have done at some point. Everybody has done a Grignard reaction, or at least knows one. What's your temperature usually of a Grignard reaction, let's say, to sensitive system? If you're going to run this chemistry because you had a sensitive functional group in it, what would you normally do to execute this reaction more selectively? Would you run it reflux, cooling? Okay, what's your normal temperature, bench top, nothing else? What would you typically do? You only have like 2 or 3 would you typically use? Yeah, minus 78, 0, or what's liquid nitrogen? Much colder. Why is it minus 78? Why do we use minus 78?
Because that's dry ice.
We have a physical phase transition of dry ice, right? These are convenient parts we actually end up doing. Okay, let's say we're running a Grignard at minus 78 degrees, and you want to take by TLC and sample what happened in that reaction. What do?
Just reach out a little bit of your compound.
Okay, and then
You run a mass spec.
run a mass spec, but it warms up.
Yeah.
The entire time you pick it up, you have a smaller volume material, heat transfer is now relevant, you're not cooling that sample, the reaction runs to completion. Roughly 16 months of my PhD was painfully learning that lesson, that things work up and complete when you sample them. So what's in the pot has nothing to do with what you sample. So this is where understanding the limits of your technology, of what that measurement actually means and why it's relevant to your system, is absolutely fundamental. It's the biggest part of what I do in my research, and it's something I want to teach you guys into. And again, it comes back to assumptions. If that piece of TLC data told you the reaction is complete, you are making an assumption that what you put on the plate is indicative or some representation of what's in that reaction. So do you guys have a solution to that? Imagine your world is only TLC. What do you do to prevent that? What are the strategies you might be able to apply to still be able to use TLC, get an accurate measurement without the possibility of it working up or finishing completion when you sample it?
Quench somehow.
Okay, give me an example. Quench is good. Does anybody have to do this yet? Again, not a problem now, but this is an exercise I want to work through in this point of coming up with practical skills of way that you need to do it. Keep it cold, right? Don't make it cool, right? So that's hard. Quench it somehow, that's good. In the end, the way that we do it in our lab is we've actually built this probe that takes a sample, keeps it at the reaction temperature, isolates it from the rest of the reaction, and then introduces a quench. So we protonate it, or we add an electrophile, a sacrificial component, so we react it to turn into something else. But then there's other layers in this too. What if the Grignard reagent you're doing has no UV chromophore? Okay, I can't use HPLC now. Or I have to add that chromophore in the quench, right? This is where all the tools that we have that go into synthesis have to be applied into reaction analysis. And it's all stuff that you know, you're just bringing them into different components from different parts. One thing I love doing, and this is why I love real-time analysis, with our tools we can have things like these concentration over time trends. These are the major components that we get to see. But one thing that we end up doing by having real-time analysis is you can go back to the data and mine it for things you didn't think you needed. So what I'm showing over there on the side is going down into the baseline of an HPLC that's been recorded real time. The major components were those big things, but I can go and look in the baseline and find that there's these other trends of minor components. And if I just took that sample and threw it on the HPLC, I might see these blips and go, garbage, waste material. I don't know what it is. Having a time course associated with these minor components gives you, I used to call it when I first got to use HPLC MS, it gave you the hope that it was worth the time to figure out what the heck that thing was. You know, a blip might just be a blip, but if you've got a blip that is changing with the same time frequency as a major component, or even better, something that shows up and then tanks right at the same time as the reaction ends, that means something. Has anybody ever seen, I apologize, I use way too many references from bad movies. Have you ever seen Close Encounters of the Third Kind? He gets it. Go and look at it. There's a meme. This means something. Close Encounters of the Third Kind is some movie where a guy gets abducted by aliens. At one point, he's playing with, like, he's scooping up mashed potatoes, and he does this moment where he's, you know, he knows that this is important. He starts shaping the mashed potatoes like a mountain, and his only point is he's staring at it like a madman going, this means something. That's most of our day. You don't know necessarily what it is, but I'm hoping I can train you guys the intuition that says, spend the time to figure that out because it matters, right? Okay, course-specific stuff. This is the main textbook we will be using. We are not going to be going prescriptively from it. This is a good resource. There's actually not a lot of good standard issue textbooks for physical organic chemistry. This is probably one of the better ones. You do not need to buy it. If you have available onto it, there are a couple. You can find it online. I'm sure there's a free PDF of this if you don't want to actually purchase it. But it is a decent resource for a lot of the other background material and stuff we're doing. A lot of the stuff I'm going to be discussing is actually from more common and modern literature, including reactions and stuff that have come from my lab, but it's based off a lot of the technology and stuff from this. Major things you will need. Absolutely. Right now, when you get home, go to copasi.org and download Copasi. Copasi is a free modeling software for reaction network predictions. We will go through this in a tutorial. Has anybody used things like kinetic modeling software ever? There's a couple of different packages. Copasi was actually built by biologists in order to model enzymatic pathways to basically come up with concentration timed curves. I'll show you guys how to use it as a direct tutorial. We'll actually spend a couple of classes directly on it, but immediately please go download it. Make sure it's working on your PC or Mac or whatever component. You can take a quick spin through it. There's some really good online resources for using on YouTube of how to do certain parts of it, but we will go through this in class. Jupyter Notebooks. Has anybody used Python and Jupyter Notebooks? Again, we will have an opportunity. One of my graduate students will come and do a Python primer. We are not going to be using Python. It is an accessory tool that you can use for things like computation. A lot of the things that we end up doing, if you have sort of an idea of a particular mechanism, you can put it in something like Copasi and basically say, if I'm right, this is what the reaction should do. It's really powerful from that kind of hypothesis generation and testing. Jupyter is just really good from a very light way to run very simple Python code. If you've not done things like, if you'd hate doing linear algebra, you can use and rely on things like Python to do a lot of that grinding for you. Longhand is not the only way. I will show you some of this components of what I like to do. Again, this is just more of these are tools for things like graphing, data manipulation, and just data science that are very useful, but not required. This is required. Current literature, everybody should be familiar with JAX, ACS Catalysis, Angewandte, ChemSci, and React Chemistry Engineering. The other major one that I like using a lot too is OPRD, Organic Process Research and Development. So this is the process chemistry version of it. Keep up with these articles. This is just a good news. You guys should be doing this, especially as graduate students and senior students. This is what's happening in the literature right now. In particular, if you're interested in anything to do with catalysis, the most modern stuff that's happening is out in these journals. For the next piece of what we're going to be doing here, so content, this is the rough battery of topics that we're going to cover through. And like I said, I will try to emphasize or again change the order a little bit depending on people's interests. So I do need to hear from you in terms of other feedback. The major three things that we're going to do for grading. So final, we will have some final. It'll look like some component of it, and ideally what this will be is everybody's together in a room, you'll be given an assignment, which is usually work through pieces of data. Do not think of this as essay generation. It'll be something more like, here is a problem, given your computer and the tools that we've presented in the lab, come up with a report or understanding of a reaction mechanism. The class presentation, I'll go to that in a little bit more detail. This is something where I want you guys to use this as a topics part to tell me about what types of things you're interested in, and based on these types, go find an article that applies one of these methods in that article. So based on 2024 and forward, the last year and a half, find an article that understands or does a mechanistic interpretation using, for example, kinetic isotope theory or linear free energy relationships in order to do a mechanistic point. So it's applying the kinds of topics we're doing in some sort of a research article that you're going to pull. The midterm will be take home. It'll be roughly, I think we scheduled it for, so this is the class presentation part first. After we're finalized in terms of the total part of the course, I'm going to finalize the dates for this. So what I will do is if there's 20 people in the class totally at the end, we're going to take about 10 lectures, one person per lecture for the very last couple weeks of class. So basically from the 12th to the 7th, based on our 10 lectures, those will be when we're doing class presentations. So you guys will have to select the paper that you choose to do, send it to me. I will say, yep, this looks like a good paper. You have from the 4th to whatever your time slot is in here, and again, I will finalize those by the end of January of when you will be presenting. If that conflicts with something else that you have, let me know in advance and we can reschedule it. But it's the important thing is we'll get that part together. The major thing of this is not only just, okay, it's me at the back of the room listening to what you guys have, you guys will be self-evaluating. Part of what I want you to do is not just what did you think this your colleague presented, but also what is your engagement. I expect you guys to answer questions based on what you are bringing. So you guys pay attention to the lecture, and I want you to either answer questions that you should have understood because the person taught it to you, or you guys are asking questions of the people that were at the front of the class. So this is meant to be a full class engagement. Think of this like journal study, effectively, right? The basic structure, it's gonna be about a 20-minute presentation. Has anybody ever heard of this structure? SCQA, Situation, Complication, Question, and Answer. This is a structure that we use in my group for any type of communication. This is research articles, this is presentations. When you're putting something together, you should try to think of it as you're going to spend about 2 or 3 minutes as introduction laying out the situation of that paper. So that could be, what's the background? Why is this your research topic? You bring in everything relevant to that. So it's not just this particular paper. You may have to go back and say, I'm doing this on proline catalysis, and this is where it comes from, where it's been applied, and why this thing matters. The complication is meant to be, why should you care about this paper? This is what's different laid out by whatever the situation is. Then you're going to spend about 1 or 2 minutes saying, why is this paper relevant? What is the novel strategy that this paper or research team is employing, and why should everybody out here care about that particular one? And then you go into the detailed answer. What are they trying to present? What is this data? And you can be, I've put up a couple of other examples online. I'm happy to provide others from previous year. But you can actually, don't think of this just as a book report. You don't have to come here and say, this research team is presenting this catalyst that apparently addresses this problem, and here's what their data says. You can sit there and say, I do not agree with their data, because it happens, and that's actually a big part of what we have to do, is look at the data they're presenting, look at why they said that they're doing what they're saying they're doing, and what you may look at and say, based on my understanding of what they are telling me, they did not achieve that goal. Totally legit, but this is meant to be, again, a discussion. You don't have to think of this as you're just telling people about the research article that you've chosen. Again, timeline, roughly, we'll assign the midterm on the 9th, and due roughly before midterm break. Again, these times are flexible. If this does not meet, again, you guys are graduate students in 4th year, you guys are all adults. If for whatever reason you can't make it by the 15th, let me know, we can extend it. This is meant to be an individual assessment and using of your time. While I'm expecting you guys to talk to each other, the whole line here in terms of individual work, please do not hand your file to somebody else, change the name and hand it in. If you guys work on components of stuff together, that's totally fine, but what you hand in must be your work. In other words, think of this as what you're presenting here. What you present and how you present it is your own component. Final exam will be roughly a 2-hour kind of part, and like I said, I do not expect this to be a blank sheet where you're filling in components and reactions. It's meant to be a working problem. AI is a thing. This is an area that we work into. My policy on this point too is I fully expect you guys to use this where it is valuable. Honestly, at some point, if ChatGPT, this happened before, I took the old Chem 123 exams that I used to teach and I ran it through GPT-4 and it did a pretty darn good job, which tells me I am making very bad exams, honestly. So my point is, you are fully free to use whatever AI tools that you want. The point being is this is a supplementary tool for you guys to hand in information. That's why I'm not going to give you questions which are something you can Wikipedia or something you can Google. It's meant to be working through a problem. And to that point too, if you do use a tool like generative AI to create code that you then apply, you're fully responsible for what you hand in. You guys have seen the AI lawyer stuff? No? What do you guys watch? A trial lawyer thought ChatGPT was like Google and basically asked it for legal precedent, and it very happily created precedent which did not exist. And then he submitted it in trial saying, this is why I think my case stands. You're fully responsible for that. If you hand in something that is fully hallucinated and dead wrong, well, that's your problem. He was disbarred because of this, because he handed in completely fake generated data. My point being is, we now live in I look at it this way. We live in a society where these tools are just like PowerPoint. You should know how to use them effectively. And please, if you figure out a cool way to use it, just tell me. Tell everybody else, share it with other people. The one thing I do ask, please do not post material on Chegg, credit, blah, blah, blah. The stuff we're doing here in class is really meant to be a tutorial stuff. If it's hard enough that you think you have to go to a tutoring service like Chegg, ask me first or ask your colleagues. It's a better use of your time. Same detail, more detail. Okay. Any questions before we jump into content? We're only gonna do a little bit because I have to go. Fun part about this goes, I teach this class and then I have to run across campus to go do my second year class too. So sometimes days will be a little bit blunted. Today is a brand new day, so we will be ending a little bit early so I can go over there and find out where I'm actually teaching. Any other questions though for right now? Dead simple. Is anybody at least somewhat happy that they're taking this course still? The goal is this is going to be fun. The biggest problem I think I have, what's the yes?
No, my reference finally submitted.
Congratulations. My goal is, I'm a giant nerd. I hope you guys like some of the stuff that I like at the end of this. That's the kind of the main target of all this. Again, pause for other comment. Anything else that you guys want to ask at this point?
Are the class presentations group or are they also?
Excuse me?
The class presentations, are they group or can we do it
Individual, yeah. One per, the goal is, so again, let's say, are we 20 now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 20. Woo. Goal is we will roughly have 10 classes, 2 lectures, or 2 students per class, and we'll set them up based on rough timing. Again, I'll set the schedule randomly. You guys let me know if you have a conference you need to attend. You guys are, you're based on your TA rotations, things like that. You may have other things that are hard deadlines based on other classes. Just let me know in advance and we can reshuffle. You should have plenty of time to get that part together. And again, I posted a couple of presentations from last year to give you the style that I'm kind of looking for. I do record all the lectures. I will be posting all you get to see is this part in my voice. It's not video, sorry. I dance around too much for that. But it does mean you can review things. If you have to miss a class, that is okay. Obviously, there's gonna be a lecture recording. The problem is still, that class presentation part is more, I think of what we're doing here is very thematic based on, look, it's participation. I don't want you to sit here, absorb details and go, cool, I know how to do this. This is more practical. I want you guys to use the tools and stuff that we're trying to put in and discuss with me the type of thing we're talking through rather than just absorbing information. Anything else? Is anybody terrified? It's gonna be fun, guys. This is actually the cool part of it. And again, if I do things well, I'm hoping I can answer some questions about why things suck. Okay, No, seriously. So, kinetics. What is kinetics? It's the reason we do chemistry, is change in time, right? This is actually a first year slide that we developed that's trying to mainly impress this. You start a reaction with some one component, and then based on some segmentation in time, something is turning to something else. That's the only component we're trying to do, is just watching change over time. So you have to measure those two pieces very cleanly. And most of the time, at least when we're talking about reactions, we are talking about concentration. We're talking about components rather than individual numbers in some space, which means a big thing that you have to worry about is volume cannot be changing. Temperature, pressure, a lot about the reaction have to be roughly held constant. And that's actually a major problem that we have, is a lot of those basic held assumptions don't work in even some very basic reactions. So reaction progress ends up looking like this. It's the moment by moment change over time that we end up getting. Now, if you look at a graph like this, what are we implying? What is already, give me some conversation. If you've been presented with a piece of data like this, what is this trying to communicate to you?
That A turns to B and only B.
A turns to B and only B. Good. What else do you got? What are the dots?
Measurements of
These are probably actual pieces of experimental data, right? What's that?
That's
interpolation.
Usually it's an interpolation. You're saying there's a reason that this goes to this with this shape. And that's also, you look at something like this, even the curvature you apply here, that means something. Why? What are we saying when we've done, instead of just drawing a straight line to here versus that curvature, what are we implying? Rate changed. Rate changed either way, each of these sections, right? So where on here is rate, by the way? Slope of what?
Concentration over time.
Okay, more specific. There's a lot of different rates, right? So first of all, rate is time dependent. During parts of this reaction, the rate is changing because the tangent, the slope of the tangent for each of these components is changing over time. There is a rate of A going away. There's a rate of B coming in. The other thing that's implied here, not just from this chemical equation, but if you did the math here, what do you think would happen if I added this plus this, or this plus this, the entire way through? What do you think I would get? Which is?
I guess 1 is
But what do you think it is? What do we call that? That constant matters. That's something very important for any reaction. Mass balance. We're assuming that the first law applies and that matter is not created or destroyed. It has to go somewhere. So your number one goal as a kineticist, as a physical organic chemist, is you're playing a detective. This is ideal. 99% of the time, it will not look like this. You're missing something. And then, like, honestly, the number one thing you can do is if you made a measurement like this, go be an accountant. Figure out what you are missing and where that mass went, and that will point your way most of the time to whatever the heck went wrong. Find your material. It doesn't just go into anything else. The shape of the curve is trying to communicate a bunch of different things. We say on top, that is slower and this is faster. Now give me two important features of these reactions which match these statements. Why is that one slower and this one faster? What is something analytically you can look at those graphs and tell me about?
the slope in the first part of the graph.
Okay, slope in the first part. Not just that though. So first part of the graph might actually be identical, in which case the rate here initially might be the same, but more broadly, looking at the entire part, what else do you got? You're right, the initial rate is an indicator, but there's a bunch more. Yeah.
There's more product formed at the 60-minute.
At the common time, there is more of a product, right? If we pick the same time point anywhere through here, the percent conversion of one or the other is higher, right? There's more product. That implies also we've got to be really accurate in our product concentration measurement, true. Now, this is something else. Has anybody done what's called LCAP or LC area percent or percent conversion? Have you ever heard of percent conversion? Yeah? Percent conversion is saying, maybe I didn't get this measurement correct, or this measurement, but I'm going to ratio the two. Why that's important is it gives you an internal measurement where you might be off in terms of your concentration. if this was HPLC, your alpha value, your epsilon, right? Your extinction coefficient may not be accurate. Cool thing about that is this point right here matters because that's your 50% conversion. It's the point where you're transitioning from mostly starting material to mostly product, and you can take a line and say, that happened here at, call it 10 minutes, and over here, 25. So the physical time we transition from one to another, that's things like half-lives. That's why we use these other relative measurements where internally in the data set, you can quantify them against each other. But you're right, these are things implicitly we can go through, and there's a bunch of different ways to look at it. When was the last time people did kinetics?
Last term.
Last term? I saw it cringes. No, I mean it. Like, again, this is a safe space. When was the last time you guys did kinetics? Last term. Which course last term?
Biochemistry 402, so enzymology.
Okay. You guys?
2020.
2020? Great year. It's okay. We are going to go through sort of a deep revival. I'm starting back basically at first year kinetics, and we'll kind of build up from there. The major thing I want to do is actually take on some commonly held misconceptions. Does anybody know about what's called initial rate for extraction order? Yeah, by the end of this week, I hope you will never freaking use initial rate for anything ever again. And again, part of that comes down to that you've been told and used tools that make sense. This is common. What I want you guys to have is tools like this, plus things like Copasi, where you can go a little bit deeper into that analysis. All right, that's where we're going to break off today. Again, you got the course website. Canvas should be online. Please make sure you have access to it. That's where distribution of the slides, the recordings, everything else is going to go through that. So please take a look at that. Shoot me an email if you have any other questions or comments until now. After that, again, like I said, probably end of the week, we will have a first draft of when people are doing which lectures. Download capacity. We will do a thing on that on Friday for sure. See you guys.